Now we're going to take a look at how to calculate the length of the part of a parametric curve. This is something that you've already have seen in the case of the graph of a function in Calculus 1. You should have established a formula to calculate the length of a piece of the graph of a function. And we'll see that this is a particular case of the formula for parametric curves. So we have a curve, a parametric curve, in this case given by parametric equation x is f of t and y is g of t for t in a closed interval, let's say ab, and we want to calculate the length of the corresponding curve. There are basic assumptions that we should make in order to calculate this length. To start with, let's say here is a point when t equals a. We should assume that we traverse the curve only once as t increases from a to b. So we have this kind of situation where the curve is traversed once as t goes from a to b. If we were going back and forth on the curve, of course, we would have some parts of the length counted several times. So among our assumptions, the general setting will be that the curve C is traversed exactly once as t increases from a to b, and additionally we're going to have some technical assumptions, namely that the curve is a smooth curve, or what we will call a smooth curve. That is, the functions f and g defining the coordinates x and y are differentiable, continuous on the closed interval, differentiable on the open interval, and their derivatives are also continuous. So to calculate this length, we're going to use an approach that is very similar to what we have done in the case of the graph of a function, which is simply to approximate the length by something we know how to calculate, namely the length of a polygonal curve. So we pick sample points on the parametric curve, and that corresponds to taking a partition of the interval of time, where here time is a parameter. So we cut the interval AB into pieces, starting with t0 at A, and then t1, t2, and so on, until tn, which is B. And to these sample values of the parameter correspond points on the curve, and we're going to join these points on the curve and obtain a polygonal line that whose length can be calculated. And the approach will be to increase the number of points on the curve in order to get a better and better approximation of the actual length of the curve by the length of a polygonal line, for which we can do calculations. So how do we calculate the length of this polygonal line? Of course, the length is going to be the sum of the lengths of each line segment that joins two consecutive points. And to do that, we're going to focus on one and zoom in on that and see what we can do. So between two consecutive points tk and tk plus 1 in the partition of the interval AB for the parameter, this is a kind of picture we have, and of course you can consider this right triangle where the base is delta xk, and that's the change in x value as t changes from tk to tk plus 1, and delta yk is going to be the change in y value as t changes from tk to tk plus 1. And because this is the right triangle, of course, the length that we're seeking, that I will denote by L indexed by k, is simply the square root of the sum of the squares of the two sides, because we have a right triangle, so we can use the Pythagorean theorem. Now delta xk square plus delta yk square is something that we can reformulate, because delta xk is a change in x values, in other words the value of f at tk plus 1 minus the value of f at tk, and similarly for delta yk, the change in y value is the value of g at tk plus 1 minus the value of g at tk. Now we have assumed that f and g are continuous on the closed interval AB and differentiable on the open interval AB in particular. So in particular, they have the same properties on the interval from tk to tk plus 1. And these are the assumptions we need to apply the mean value theorem, which states that under this assumption, the average rate of change of the function over the interval is a value that is taken for the instantaneous rate of change. In other words, the derivative of the function takes somewhere on the interval the value, the average rate of change of the function. So one way to write that is that for some sample point tk star that is between tk and tk plus 1, the derivative takes the average rate of change of the function as a value, which means it takes a value f of tk plus 1 minus f of tk over tk plus 1 minus tk. This tk plus 1 minus tk is change in t when we move from tk to tk plus 1, and I'm going to write that delta tk. So this delta tk is really tk plus 1 minus tk. And similarly for g, we have the same assumptions, and therefore we can also apply the mean value theorem to the function g on the interval from tk to tk plus 1 to the effect that there is another point tk star star between tk and tk plus 1 where the derivative of g takes the average rate of change of g over the interval as a value, which we can write as this delta yk is g prime of this tk star star multiplied by delta tk. So replacing this inside the formula for Lk, we get the sum of the squares of these two quantities, and you see that the sum of the squares is now going to be f prime of tk star square multiplied by delta tk square, and then we add g prime of tk star star squared multiplied by delta tk squared. We can factor out the delta tk squared and then pull it out of the square root in the formula for Lk, and this is what we obtain. So this is for the length of just one line segment joining two consecutive points on the curve in the partition that we have designed here. If we put that together for the whole curve, we get the line of the green polygonal, the length, sorry, of the green polygonal line is the sum from 0 to n minus 1 of the LKs, which of course is the sum from 0 to n minus 1 of this square root of f prime of tk star squared plus g prime of tk star star squared, all this multiplied by delta tk. And so as we increase the number of sample points, as we increase the number of subintervals for the partition of the interval of the parameter, right, we're cutting the interval AB, the interval for t, into subintervals, and we get a sum that depends on two sample points in these intervals. I have written here that this should approach L as n goes to infinity. It's a little bit of a shortcut to say n goes to infinity, because really this should be as a limit as over all partitions where we pick two sample points inside each subinterval, and as a parameter of the partition goes to 0. But in any case, you intuitively should see that as we increase the number of subintervals, we get a better and better approximation of the actual length of the curve. And so we should look at this sum that we have on the right hand side. You see that it looks like a Riemann sum for the function square root of f prime squared plus g prime squared, but it's not quite the case, because we have two sample points. We have this tk star, which is a sample point in the kth subinterval, and tk star, which is a second sample point in the same interval. So because of that, it's not quite a Riemann sum. Nevertheless, as the parameter of the subdivision goes to 0, here I have symbolically written as n goes to infinity, in the sense that we increase the number of subintervals. But as I said, it is a little bit more complicated than that. Anyway, it is not hard to believe that as we increase the number of subintervals, in other words, when the maximal length of the subintervals goes to 0, this is going to approach the integral from a to b of the square root of f prime of t squared plus g prime of t squared. And so this is what we're really going to take as a definition of the length of the curve. So in this setting, where the curve, the parametric curve we're considering, is traversed exactly once as t increases from a to b, and the curve is smooth, then the length of the curve is given by this integral that we have just seen, which we can write as the integral from a to b of the square root of the sum of the squares of the derivative of x and of y. Derivatives, of course, with respect to time, to the parameter. Now we may take a look at the case that you knew before, the case of the graph of a function, y equal f of x. And to apply this formula to this case, we need to consider the graph of the function as a parametric curve. And this is easy to do because I can, for x, call x a parameter, so say x equal t, and then y is f of x, in other words f of t. And the parameter t here, of course, if we're looking at the piece of the graph that lies above the interval where x is between a and b, that means t, which is the same as x, is also between a and b. So if we apply this formula, the length of the corresponding part is going to be given by this integral from a to b of square root of the sum of the squares of the derivatives of x and y. And you see that in that case the derivative of x with respect to t is going to be 1. When we square it, we still get 1. And dy over dt is f prime of t, but of course, since t and x are the same thing, this is really just f prime of x, and dt is the same as dx. So we obtain that the length is the integral from a to b of the square root of 1 plus f prime of x squared, and we integrate that with respect to x. And this is exactly the formula that you had established in Calc 1 for the case of the graph of a function.